Hello and welcome to my last installment for the day. Um, I have shown you how you get your standard error of the regression, which is actually the standard error of the error term. And using it, you are able to get the standard errors for estimated coefficients. I have shown you how to get your R squared, which tells us the proportion of variation in the dependent variable that is predicted or explained by your dependent variable or by the model, if you like to put it that way. Now, what I want to do now is to show you how we can generate a statistic that judges the overall performance of the model in terms of explaining the phenomenon of earnings variation that we want to explain. So for us to be able to, the intuition behind the statistic is something like this. We want to take a ratio of what we managed to explain relative to what we failed to explain. Okay. Now, if we assume that we are rational, as we ought to be, surely it is in our best interest to have the numerator being bigger than the denominator. That is, here what you are saying is this is what the model has managed to explain is what we're calling the explained sum of squares, and what the model has failed to explain is the residual sum of squares. So what you want is to make sure that the numerator is much bigger than the denominator. That is, we want our model to explain much more than it cannot. Okay, so that's the idea behind our measurement of how good our model is. A model is good if it can explain a lot more. That is, if the ratio of what it can explain to what it cannot explain is a very big number. Okay, put it that way. So now, for us to be able to do that, we have to work with this information we already calculated earlier on. Now, the question is, we can put the degrees of freedom here. Now, what we failed to explain, here's the following degrees of freedom: the sample size minus the estimated coefficients we used to generate the explanation. Okay, so the estimated coefficients were only 2, so that's n minus 2. Okay, so in general terms it will be n minus k, where k is the number of estimated coefficients. Okay, and your ESS here, you can think of it in you can think about its degrees of freedom in two ways. Either you can say the number of explanatory variables we have. For example, in this regression we only have one explanatory variable, so we would put it there. But you can think about it as well in terms of the number of coefficients we have estimated. So we estimated k coefficients where k is 2, but we must remove one of those estimated coefficients, which is the constant, because it is not an explanatory, it is not associated with an explanatory variable. It's just a geometrical construction we put there to be able to fix our line. So the slope coefficients are what we are interested in. They are the ones that tell us the impact of the explanatory variable on the dependent variable. So we less 1. Now, from what we have, this is 50 minus 2. We had two estimated parameters, that is the intercept and the slope coefficient, right? And here we had two estimated coefficients less the intercept, which is 1. So you can see that this will be equal to 1. So it's two estimated coefficients less the intercept. Why is it? I just want a number there. Okay, so it was not putting dates. So let's do the same here. 50 minus 2, which is 48. Okay, now here we have used the data. Before we did everything else, we used the data to calculate only one sample statistic called the mean. Okay, so n minus 1. So this is 50 minus 1 equal to 50 minus 1, which is 49. So if you sum these two, you should get that. Okay, now notice here our explained sum of squares have only 1 degree of freedom. Remember, I said we can think of this in two ways. How many explanatory variables did we use to explain variation in earnings? We only used 1, and that's why we have the 1 there. If I had 2 variables in this regression, that is education and experience, then the situation would be different here, because then it would be 3 estimated coefficients minus 1, and it would be 2, right? And this 2 is actually speaking to the number of variables we used to explain earnings. We use the education and earnings, which is 2, right? But for now it's 1 because it's a bivariate regression. Now, once you have all this information before us, we can do a lot of wonderful things with this information. Now, what we need to do is to adjust these numbers here for their degrees of freedom, which we have there. These are the degrees of freedom we have calculated. So we need RSS over its degrees of freedom, which is n minus k. This is also called the mean residual sum of squares, which means we have adjusted that for degrees of freedom. And this will be equal to that number there divided by its degrees of freedom there, and we get that. You remember, this is the variance of the error term. This is also the variance of y in your regression. Then your explained sum of squares over k minus 1 is your mean explained sum of squares, and or regression sum of squares, and this is equal to this number here over that, which is that. Then your total sum of squares over n minus 1 is also called your mean total sum of squares, which is equal to that number there over 49, and you get that much. Right, but you actually don't need the last one here. It's not, it is these two that we actually work with to derive everything we need, so we can leave this as is. Right, so now our F-statistic, which we use to generate a measure of how good our model as a whole is equal to your mean explained sum of squares over your mean residual sum of squares. Okay, and this is just equal to this number over that number, and you get this number 12.81. If you come here, you will see that you have it there. That's 12.81728, 12.81728. If I reduce the number of decimal places for you, you can see that is the same number. So essentially that's what you do. Of course, you can complete this just to make sure you don't get lost. So it's actually ESS. Let's use corner brackets. It's ESS over K minus 1, right? Close your bracket over, open another corner bracket, RSS over N minus K, close bracket. This is what we were doing here. That's what we were doing. Let's bring that back. Our stuff is hidden now. Okay, that's what we were doing. So in your formula booklet, you might see a formula like this. That's what you will see in your formula booklet, where K is the number of variables, the number of estimated coefficients, and the minus 1 there is taking away the constant. Now, this F can also be estimated as, remember that by virtue of us having ESS there and our RSS there, in a sense what is happening there is we are involving the R squared. The R squared is actually involved in all this. Remember that your R squared is given by ESS over TSS, or 1 minus RSS over TSS. The fact that the numerator and the denominator contain ESS and RSS implies that we can easily arrive at the F using the R squared. So what we're going to do, instead of showing you the algebraic manipulation, I'll just put it very simply. So this is equal to what the model managed to explain, which is measured by our R squared, the proportion that our model can explain, over the respective degrees of freedom K minus 1, divided by what our model failed to explain over the degrees of freedom N minus K. Okay, you will have a formula like this in your booklet. So what is that? So this is equal to, let's have that, I will have two brackets. Okay, just one. So this is our R squared, you remember, that's the R squared, over our K minus 1, our numerator degrees of freedom K minus 1 is 2 minus 1, right? It was 1. We close that, we divide by 1 minus our R squared. We close, and we are dividing this by N minus K. Our N is 50, our K is 2 estimated coefficients. We close that, okay, and we say okay. You see it's the same number that you get there. So what it means is, if you know your R squared, you can find the F. If you are given the explained sum of squares, the RSS, you can find your F. Whichever way, you can find the F. So this is the number we have here, which is the F. So this is the statistic we use to measure how good our model is overall. So overall, for us to be able to say that, we have to compare what our model explained to what it failed to explain. The bigger that ratio is, the better the model is. So we want what it managed to explain to be far bigger than what it failed to explain. That's the logic behind the F. That's all we have done. So now I think we are ready to go into hypothesis testing and all these other things, because we now understand all these output. Everything is linked to everything here. We know how they are computed and all those things. I will stop here.